So let me begin the recording and we will go to this example. This is from this document, okay? The Blease uh, document that we have been referring to. And let us go to chapter number 5 of this document, multi-level models in R, which I have uploaded, right? Multi-level modeling in R 2.7. Okay, this is by Paul Blease, uh, 2022. And we will go to chapter number 5 now, growth, data structure, growth modeling, repeated measures, data. Now let us read this together and then we'll look at example. Growth models are an important variation of multi-level models. In growth models, repeated observations from an individual represent the level 1 variables and attributes of individuals represent level 2 variables. So we have read this already. The fact that L1 variables are repeated over time poses some additional analytic issues. However, the steps used to analyze the basic growth model and the steps used to analyze a multi-level model share many key similarities. Okay, now let's look at methodological challenges. Since longitudinal data is collected from single entities over multiple times, it is likely that there will be a high degree of non-independence in responses. So we have done this already. Multiple responses from an individual will tend to be related by the virtue of being provided by the same person. And this non-independence violates the statistical assumption of independence underlying many common data analytic techniques. Issue about non-independence, let me first delete it and read this together. Issues about non-independence are similar to those that occur when working with lower level data nested in higher level groups. In longitudinal designs, however, there are additional complications associated with lower level responses. First, it is likely that responses temporally close to each other, for example, responses 1 and 2 will be more strongly related than responses temporally far apart. So I told you this, we were discussing this before the break, that my job satisfaction at time 1 and my job satisfaction at time 2 will be strongly or relatively more correlated than my responses at time 1 and time 4. This pattern is defined as a simplex pattern or lag 1 autocorrelation in the residuals. Second, it is likely that responses will tend to become either more variable over time or less variable over time. For instance, individuals starting jobs may initially have a low degree of variability in performance, but over time the variance in job performance may increase. In statistical terms, outcome variables in longitudinal data are likely to display heteroscedasticity. Okay, let us highlight this word. To obtain correct standard errors and to draw correct statistical inferences, autocorrelation and heteroscedasticity both need to be incorporated into the statistical model, and this is done at lower level responses, L1 responses. The need to test for both autocorrelation and heteroscedasticity in growth models arises because the level 1 variables repeated measures from an individual are ordered by time. One of the main differences between growth models and multi-level models revolves around understanding how to properly account for time in both the statistical models and in the data structures. Okay, and so let us go to now our example. Okay, let us look at this first example. So I am now going to change my working directory, and instead of multi-level, I am now going to work in longitudinal folder. Okay, I open, and we will start with this longitudinal.r data file. Okay, that I had mailed you today morning, all of you. We will use this longitudinal.r. This is also uploaded in the shared drive. Okay, we will work with this longitudinal.r script. So we have set our working directory to longitudinal, and we are now working with our so we will set library multi-level. Okay, and this univ bct, this data file is available in this package. So let us say data univ, and now I am also going to clear my environment because I am going to work with longitudinal data. So let us start with unit data unit bct. Okay, and if I open this data file, it's a big data. Okay, it has battalion, it has company, then it has marital status, gender of the cadet, how long that individual has been working, what is the rank, what is the education, what is the age. Then we have taken job satisfaction at time 1, okay, commitment at time 1, then readiness at time 1, job satisfaction at time 2 of the cadet, jobs commitment at time 2, readiness at time 2, then job satisfaction, commitment, readiness at time 3. And you see 0 1 2, these are just repeated. These three rows are absolutely common. Okay, and you see time, it has also been sorted. Time 0 job satisfaction, time 1 job satisfaction, time 2. So what was actually horizontally arranged here has now been vertically arranged. Okay, so job satisfaction, commitment, and readiness, and you have this sub number, which is actually the identifier. This is the number of the. So the first thing that I want to highlight here, that you will need to actually, when we will be doing our analysis, we will have to bring the data in vertical format. However, when you would be collating the data, you would have created a data file like this, that this is my battalion company, then this is my person's respondents marital status, gender, experience, rank, education, age. Then you would have arranged this temporally, so you would have arranged in a horizontal row, right? You would have arranged it in a row. But when we will need to do this analysis, we will have to bring this in this format, where you will have to do this 0 1 2 and so on. Okay, so this is something that we must keep in mind when we are so this is data preparation, essentially how we will have to prepare our data file. So I have written this also. I have given a comment. We can write this in a CSV file, okay, which is also uploaded in the folder. Let me show you this univ in the longitudinal univbct.csv. This file is already there. This complete data has been written. Okay, in case you want to. This dataset contains 3 measures taken 6 months apart. So this is what Nivedita was asking. Job satisfaction, commitment, readiness. Okay, these are variables that don't change every day, so they have taken it 6 months apart. It also contains some stable individual characteristics such as respondent gender, marital status, and age at the initial data collection time. That is at time zero. What was the gender, marital status, age? These latter variables are treated as level 2 predictors in subsequent modeling. So there are three time points. Okay, so you have job satisfaction, for example, varying at three time points, and then you have L2 variables, which are gender, marital status, and age. This is a between subject variable. Okay, so what are the number of rows here? 1485, and unique, there are 495. So this is unique. How many unique sub numbers are there? 495. So you have 400. This data of job satisfaction over three time points was collected for 495 cadets or people. Okay, this is what I have written. Now we have to create a multivariate data set out of the UNIV BCT data frame. We select every third row of the UNIV BCT because there are these rows that are repeating. So I have to select every third row which is unique, right? So I create grow dat and I say 3 into 1 colon 495. That means do it for every third row. So 1 multiplied with 3. So it will be row 3, then row 6, row 9, up till row number 1485. And then what are the columns that I want? I want the column number 22. So let me show you what is column number 22. This is column number 22, sub number that should come first. Then I want column 8, 9, 12 and 15. 8, which is age, 9, which is job satisfaction at time 1, job satisfaction at time 2, and job satisfaction at time 3. So I call this as, I run this command and you will see a grow dat has been created. Growth data. You have sub number, cadet 1, age of the cadet. Okay, this is the between subject predictor. And then you have the job satisfaction at three time points. Okay, so I have just created this data frame that we will be using for subsequent analysis. And so I have written here back and I say please growth data horizontal.csv. This is also there in the folder. You can see this is subnum, age, job satisfaction 1, job satisfaction 2, job satisfaction 3. Okay, now there is a command in this package which says make univ, because the first step is we have to, this is horizontally arranged. This is how we will actually arrange when we are collecting our data. But in order to do the analysis, you will have to sort it like this: time and job satisfaction. It should come in vertical format. So from horizontal we have to create vertical. Okay, so how do we do this? The command is make univ. You say growth data, and then what are the rows or columns which have to be arranged vertically? Column 3, column 4, column 5. So grow dat, and you have to arrange columns 3, 4, 5. So let's do this univ.grow. And now the moment I do this, I see that there is, so it creates a time variable 0, 1, 2, and it also creates a multi-time dv, okay, dependent variable, which has, it has done nothing but arranged job satisfaction 1, job satisfaction 2, job satisfaction 3 in a vertical format. So 1.666667, 1 and 3. It has been arranged in a vertical format. Okay, and I have written it back, and this is also available in the folder that I have shared. This is the vertical data file. Okay, this is something that we will be using, and you see age has been repeated because this is a between subject variable. So for subject 1, age has been repeated 3 times. For subject 2, the age has been repeated 3 times, and the same thing for everybody. Okay, so now we go to our R script, and this is a command where I am going to plot. It says multdv, plot it with time and do it for every subject, and I want to plot it for first 90 rows. So you say I have written data is equal to univ dot grow first 90, row number 1 to 90. Okay, and I say color blue, different color lines. Okay, and let's see, label time and job satisfaction. So I run library lattice, and when I plot this, you will see a plot like this opens up. So these data points are colored as blue and the line is colored as black, and this has been done for first 30 subjects. Okay, first 30 cadets, and we can see that a line has been estimated, and we see clearly that there is a random intercept as well as random slope in this data, right? Very clearly there is random intercept and random slope. Okay, so we come to our steps now. Okay, the first step that we are going to do is what we call as a null model, and the command is lme, and what is the output? Variable multdv is regressed over 1. Okay, intercept, and random is also 1 random intercept, and it varies for subject number, subnum. Data is equal to univ.grow. Okay, if there are some uh, 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 missing data, then you omit that, and you have your method, right? This says if there are missing data, please omit it, na.omit. So if we run this, this is our first step, null.model, and I get variance covariance. Okay, var_cor. So for intercept it is 0.4325, for residual it is 0.4319. So interestingly, you see in this case our ICC1 comes out to be 0.50. That means we can say 50% variability in the data can be attributed to individuals. So we say ICC associated with job satisfaction is 0.50. This is ICC1. This indicates that 50% of the variance in any individual report of job satisfaction can be explained by the properties of individuals who provided the rating, by the characteristics. Okay, properties is maybe not a very good word here. Characteristics of the individual who provided the rating. That means it is because of the individual. 50% variance is because of the people who responded, who were doing it. Okay, so we computed our ICC1, and now we move to our next step, which is we want to model whether there is a linear trend or a quadratic trend, because there are 3 time points. So we can model a linear trend or a quadratic trend. That's the second step. whether this is a linear change over time or a quadratic trend over time. So this is, let me just show you where are we. So I have written what are the steps in longitudinal analysis. The step 0 is preparing the data file, rearrange from, this is, as this is, let me correct, it should be horizontal to vertical, not vertical to horizontal. Let me correct it right now. We have to rearrange from horizontal to vertical format. So longitudinal data in univariate form, subnum 111, 012, and 3.4, 3.6, 3.3. This is I have taken these from these documents, and you have 1485, and it has been arranged. Estimating unilevel equation. If you want to estimate, this is for for one individual we can plot, okay, overall, but I have not done it, and I show you that actually there is random intercept and random variance. So one unilevel equation is not a good thing to do, and we need to actually move to multi-level equation. So this is what I have written. The next step is modeling growth in time per subject. Okay, random intercept and random slope. First of all, we'll see whether there is a time trend, if there is a linear trend, or there is a time square. Then we will see whether this can be explained, whether there is a change in random intercept and random slope. This is eventually where we want to come to, right? So first let us check if there is a linear trend or a quadratic trend. So what will I do? I will go to, if you want, I can write the equation also, just to make it clear for everybody. So let us look at our null model. What were the equations? Our null model equation were job satisfaction Ti is equal to pi 0 I plus Ri R Ti, and I say pi 0 I is equal to beta 0 plus u0. So we say it becomes job satisfaction Ti is equal to beta 0 plus u0I plus RTI. So our LME command was multidv, which is essentially nothing but job satisfaction in the data file is regressed on fixed effect 1, and random is equal to tilde 1, and it varies per group, which is subnum, and data is equal to univ dot group. This was the command that we did. Now the second is, let's call this as one. Second run is linear trend, estimating linear trend in time. So what is it that we can say? We say job satisfaction Ti is equal to pi 0 I plus pi 1 I time Ti plus RTi, and we say pi 0 I is equal to some beta 0 plus u0 I, and at the moment I don't model random slope, so I keep it like this. So what is my overall equation? It becomes Ti is equal to beta 0 0 plus beta 1 0 time Ti plus u0 I plus r Ti. These are the fixed effects, these are the random effects. So what will be my command? My command is going to be mult dv, which is my outcome variable, job satisfaction, is regressed on 1 plus time. Random is equal to tilde 1, it varies per subnum, and data is equal to univ dot crop. Then I will do, let me also write the quadratic trend and we'll do it together. So we'll do quadratic trend in time. What will we say? We will say job satisfaction Ti is equal to pi 0I plus pi 1I time Ti. Now we are saying that there is a quadratic trend, so there will be time square Ti plus r Ti, and then we say pi 0I is equal to beta 0 0 plus u0 I. Pi 1I is held at a constant because we are doing random intercept, and we say pi 2I is equal to beta 20. This is also held at a constant. When we bring all of these together, we get J sat Ti is equal to beta 0 0 plus beta 1 0 time Ti plus beta 2 0 time square Ti plus u0 I plus r Ti. So these are our now three fixed effects, and these are our two random effects. So what is our command? LME, we say mult dv is regressed over 1 plus time square, because we want to test is there a quadratic trend here, and we say random is equal to tilde 1 and it varies per, and data is univ dot crop. Right, so this is what I am going to do now. I will first run mult dv is regressed on 1 plus time for linear trend, and then I am going to run mult dv is regressed on 1 plus time square. Okay, let us look at our R script now. What do? I say I am model time, and this is for linear trend. So what is the command? It says LME mult dv is regressed on 1 plus time, only one power. and random is equal to 1 varies per subnum. Data is unit.grow, NA action is NA unit. So we run this model and we do summary. And you see now intercept is significant, and every unit change in time we see that job satisfaction changes by 0.05. For every 1 unit change in time, job satisfaction is increasing by 0.05. If we compare this model with our null model, we see this has a lower AIC, lower BIC. No, actually, BIC is higher, but AIC is smaller, and deviance is smaller. Okay, and the difference is 5.69 for 1 degree of freedom, so it is significant at p less than 0.05. So we can say that model 2 is better than null dot model because our delta deviance is significant. Now you see I model the quadratic trend. The next equation on the next statement is on line number 51. I say model dot 2b, and what do I write? I say mult dv is regressed on 1 plus time and time square. Now this is a syntax in R, because you see otherwise time and time square will be highly correlated. So this notation I means make time orthogonal so as to reduce correlation. Okay, so you don't have to bother. You just remember that this is done to make time orthogonal. Okay, the two values, the two things. Otherwise, what is going to happen? I have it in the presentation. Let me actually go to this slide. Yeah, you see, I have written here, sorry, not this one. Yeah, orthogonal. So we have to make this orthogonal. Otherwise, what happens is that if you have time 0, 1, 2 and quadratic, if you just square time, it will become 0, 1, 4. So they will be highly correlated and introduce multivariate, multicollinearity issues come in. So rather than doing modeling 0, 1, 2, we have to make them orthogonal, code time orthogonally. So in SPSS, when we will come, we will have to code it manually. 0 we will code as -1, 1 we will code as 1, and 2 we will code as 1. And for quadratic, we will code 0 as 1, we will code 1 as -2, and we will code 4 as 1, right? This is done. Let me just write it here on the whiteboard. If you have time 0, 1, 2, what will be time square? It will become 1014. So the correlation between time and time square is more than zero point 0.9, actually, very close to 1, because you can see 0, 1, 0 and 2 and 4. Okay, and this will introduce multicollinearity issues. They are multicollinear in nature. So to avoid this, what do? We do orthogonal coding of time. So time and time square are coded as, what is the coding? It is coded as -1, 0 and 1, and this is coded as 1, -2 and 1. Now the correlation is close to 0, and so we avoid the multicollinearity issue. Okay, so this is a result that we have to go with, and that is why in R, right, and if you have cubic, zero, linear, quadratic, and cubic, you will code it like this. So in R, this command, this I, and in parenthesis, it is just for orthogonal coding. So we will take it as a syntax. Okay. So I have written multdv is regressed on 1 time and time square, and random is equal to tilde 1, and it varies per sub number. Let us run this and do our summary and see what do we get. We get intercept is significant still. Time is now not significant, and time square. So both of them have become non-significant actually, because we have introduced two variables. So even the time effect has gone away. And if I compare model 2 and model 2b, they are not different. They are not different. There is no significant difference in the two models. So we can say that time square we can avoid, we can remove time square, because it is neither significant nor it is actually changing the model by any means, and it is removing the effect of time also. And that is what I have written here, not significant. So stick with linear trend. So we have established now that there is no quadratic trend here. There is just linear trend. There is just time trend. Okay, is this okay? Any questions? So what is the equation now? We have, let's open a new board. Now we have established from our analysis that there is only a linear trend. Only. So this is the first run that we do, and now we can simply write job satisfaction Ti. We know for sure that it is pi 0 I plus pi 1 I time Ti plus RTI. That's it. There is no quadratic trend now. So now what we will do is we will move to the new next step, which is model random intercept and slope. We'll see if there is a significant change if we bring in both random intercept and random slope. So what am I going to write? Pi 0 I is equal to beta 0 0 plus u 0 I, and pi 1 I is equal to beta 1 0 plus u 0, sorry, u 1 I. So if we bring this together, what do we get? Job satisfaction is equal to beta 0 0 plus beta 1 0 time Ti plus u 0 I u1 I multiplied with time Ti plus R. There are two fixed effects and there are three random effects. So what will be our command? Our command will be mult dv is regressed on 1 plus time and random is equal to tilde 1 plus time, and it varies per data is equal to, right? This is our command. So let us run this now. Let us see what's the status. So I have written here model slope variability. LME mult dv is regressed on 1 plus time and random is equal to 1 plus time subnum and data is equal to unif pro. Right? So we run this and we report the, okay, we have got our effects. So time is again significant now, and we are again saying that every unit change in time job satisfaction increases by 0.05. I can also check if this is better than our previous model, and we can see that model 3 is significantly better than model number 2, where we had only random intercept. So our AIC is better, BIC is better, our deviance is significant. Delta deviance is significant. That means model number 3, where we have both random intercept and random slope, is better than random intercept only, where model dot 2 was random intercept only. Okay, so now we have established that there is a linear trend and there is both random intercept and random slope for the time. Next comes the step of modeling error structures at level 1, which we have discussed. The goal is to determine whether one's model fit improves by incorporating autoregressive structure with serial correlation and heterogeneity in error structures. So there is a command, it says autocorrelation factor ACF, and it computes this. Okay, so it shows you the plot. Time 0 with itself there is 1, then with time 1 you see there is a high correlation. With time 2 the correlation falls to very close to 0. This dotted line is telling us whether it is significantly different from 0. So it is very slightly different from 0. Otherwise all correlations are actually 0. So I can say, what am I concluding? That there is time 0 and time 1 there is a significant correlation. With time 2 I can say there is close to 0 correlation. So there is, this is what we say, and the correlations also you can report. The correlation at time 1 is about minus 0.254, which we are seeing in the plot also. At time 2 it is about 0.08, very close to, less than zero point 0.1 actually. Okay, and then 0.3 is 0.014 time 4x and so on. So how do we, what is the command in R? The command is, you say update model 3, that is the same model 3 that we had, and we say correlation is equal to correlation autoregressive structure 1 with a lag 1. That means there is autocorrelation with time t minus 1 or t plus 1, whatever, however we want to say. So this is what I have written, modeling autoregressive L1 error structure. So the syntax is, we just say correlation AR1. This is at level 1 a correlation structure. So when I say model.4a, update model.3, and now also model the L1 error structure. I run this and then summary. Okay, the estimates are about the same, nothing much. And ANOVA, it says model.4a is actually better than model.3. The AIC is smaller, The BIC is about the same. Deviance, delta deviance is 6.44 and it is P less than 0.01. Let me also take you to the presentation at this stage. So we have modeled this, okay? This we had said that there is a significant random intercept and there was random slope, right? Now let us read this together. I will share the slides. Modeling level 1 error structures. It is important to scrutinize the level 1 error structure because significance test may be affected if error structures are not properly specified. We have already seen that our residuals are going to be correlated to each other, and if there is non-independence, then the results may be impacted. The goal of this step is to determine whether one's model fit improves by incorporating different L1 error structure. This is often necessary because the error covariance matrix for repeated measures typically will exhibit some correlation between occasions. Often the repeated measures will correlate more strongly when they are taken closer together and less strongly as the time interval increases. We have seen this. Now there are different error structures and I have taken this from Heck et al. Book. There could be a scaled identity error structure where you see it assumes there is no heteroscedasticity. So at three time points, T0, T1, T2, all the variances are sigma square and there is no correlation, autocorrelation. Okay, so you can have this error structure also, L1 error structure, that at three time points my variance in the data is the same and there is no correlation between the three time point data. This L1 structure is called as scaled identity. It is the, you can say, simplest to implement but farthest from reality. Okay, then there is compound symmetry. It says that you have diagonals which are same and then you have below the diagonals and above the diagonals. Okay, so you have the same correlations between time, okay, between time points, and you have the same uh, diagonal variances. So this is slightly better, but it is still assuming you have the same variance across the three time points. There is no heterogeneity, and you are saying that the correlations are all the same. Then you can have a diagonal L1 structure which says there could be heterogeneity at three time points, sigma 1 square, sigma 2 square, sigma 3 square, and they may be different from one time point to another, but there is no correlation between time points. This is again slightly better. Heterogeneity is modeled, but the correlation is not. This is called as a diagonal error structure, which is again wrong. Then we have autoregressive error structure, which we just modeled, and it says sigma square E. So the diagonal is all same, sigma square E, and the autocorrelation coefficient is rho. So that means time 0 and time 1, the correlation is some correlation, and time 1 and time 3 it is rho square. So if rho is less than 1, let's say it is zero point 0.2, then we are saying data at time 0 and data at time 2 has a correlation of zero point 0.2. This is our correlation coefficient phi is zero point 0.2, and data between time 1 and time 2, that is time 3, time 1 and time 2 was phi, time 1 and time 3 is phi square, which is zero point 0.2 squared, so 0.04. So this is a good structure because you are saying I am modeling that the correlation is tapering off. My data at time 1 and time 3 will be less strongly correlated as compared to data at time 1 and time 2. So this is a better structure. The problem is you have the diagonal variances to be all the same as sigma square E, which is again not a very good thing because we are saying there is no heterogeneity. So there is an additional thing which says ARH1, AR1 with heterogeneity modeled. So now we are saying that the diagonal elements are replaced with separate estimates. And then finally you have unstructured, which is the most accurate, which says there are different variances at 3 time points, and then you have different correlations also. They are not equal, but it is complex because you have to now estimate how many 1, 2, 3, 4, 5, 6 different parameters. The beauty of AR is that it is estimated only by one phi. That is, so by computing one phi coefficient, autocorrelation coefficient, and one sigma square E, you can model the entire L1 error structure. So this is most reasonable, and you can say better, and you add heterogeneity, then it becomes even more accurate in our more realistic when we are doing our model. So if you look at the output, therefore you see there is a phi that is estimated. Do you see when we run autoregressive AR1, the software, so we ran this command, correlation is equal to core AR1, it estimates a parameter which is phi. Phi is our autocorrelation coefficient. So it says 0.37. That means data at time 1 and data at time 2 are correlated, and the correlation is 0.38. Data at time 1 and time 3 is going to be correlated, and the correlation will be 0.379 square of 0.379, right? So this is one, using one coefficient we can do this. And then it says model.4b, I am saying I will now also model heterogeneity in the error structure, and so the form is it varies over time. The form is it varies over time. This is the syntax, weights. So you weigh and variance exponential, form varies over time. If you do this, it is going to run and summary, and now we check. We can say the two models differ slightly. Okay, it is, well, it is not very significant. There is a small difference in AIC. BIC has actually increased. Delta deviance is not so much. Okay, it's not significant at p less than 0.05. So we can say actually heterogeneity is not, sorry, uh, heterogeneity is not there. Heterogeneity is not there, and so I have written it is not significant and will be dropped. Is that okay? So the only thing that we are going to retain in our command is correlation structure AR1. Fine. And now comes the last part, which is using L2 predictors. So let me go to my whiteboard. So we have modeled We have tested that there is random intercept and random slope. We have also tested L1 error structure. L2 error structure is by default unstructured, right? That is what we have seen here. If you see the output, it has anyways computed the standard deviation associated with u0, standard deviation associated with u1, and it has also computed the correlation. So we can say the level 2 structure is anyways assumed to be unstructured because it has computed sigma square I, sigma square S, and sigma IS. The software automatically does it by default. So we have now tested L1, we have the L2. Now comes the last step, which is bringing in L2 predictors. And in our case, there is only one. We say, does it vary per age? Does age impact this change, right, over time? So if I were to draw this, how will I draw the model? I will say age, I have time and job satisfaction. I say, can I test this? Does age impact random intercept, and does age moderate the relationship between time and job satisfaction? So what are going to be my equations? I will say job satisfaction Ti is equal to pi 0 I plus pi 1 I time Ti plus R Ti, and then I will say pi 0 I is equal to beta 0 0 plus beta 0 1 age I plus u0, and phi 1I is equal to beta 10 plus u1I. So I am first introducing age only in the random intercept. So what will I get? I will get job satisfaction Ti is equal to beta 00 plus beta 01 age I plus beta 10 time Ti plus u0I plus u1I multiplied with time Ti plus r Ti r. These are my fixed effects, these are my random effects. Three fixed effects and three random effects. So what is going to be my command? It's going to be LME mult dv is replaced on 1 plus age plus time. Random is equal to tilde 1 plus time, and it varies per and data is equal to unif dot. Okay, now I can write another set of equation where I bring in, I keep this the same and I bring in age in pi 1I. So I say beta 10 plus beta 11 age I and u0I. Sorry, u1. So what will now be my job satisfaction? It will be beta 00, beta 01 age I plus beta 10 time ti plus beta 11. Now you will get an interaction also, just like we were getting in MLM models, time ti plus you will get u0i u1i time ti plus r. So what will be the LME command now? It will be LME mult dv regressed on 1 plus age plus time plus age into time random is equal to tilt 1 plus time and it varies per subnum and data is equal to unif dot. Right, this is what we have now. Okay, so we are now going to bring in L2 predictor and it is up to you really. You can now play around with whatever predictors you want to do. Okay, so this is what I have done. I will show you with one predictor age. So I say is starting age, line number 74. What is, let me open this script again. It is line number, so I say is starting age significant in predicting intercept variation. So I say LME mult dv is regressed on 1 plus time plus age. This is only predicting at the moment random intercept. Age is predicting random intercept only, and random is both intercept and slope. Correlation is equal to AR1. I run this thing, I do summary, and you see that age is a significant predictor, that for every 1 unit change in time, job satisfaction increases by 0.05, and every 1 unit change in age, job satisfaction increases by additional 0.03. So people who are older, we can say they are significantly different in their job satisfaction than people who are younger. And then I want to see if, okay, yeah, in interpreting this coefficient from model 5, we conclude that in cases where age is 0 and where time is 0, the expected level of job satisfaction is 2.347. In some ways, this interpretation is strange because age will never actually be zero in this population. So that is why you see we do mean centering. Grand mean centering is done in order to make our coefficients interpretable. Otherwise, what is the interpretation of 2.347? For people who are zero in age and at time zero, the job satisfaction will be 2.347. Age is equal to zero is absurd because there is nobody in our population who has zero age. So therefore I have written age underscore mean centered, and you mean center it at its grand mean. So you take the mean of entire age and any NA, please remove it, take the mean and subtract the age from its mean. So this is computing age underscore mean centered. You see age underscore mean centered is grand mean centered, right? Grand mean centered. Now I will run the same command, but instead of writing age, I am going to use age underscore mean centered. Rest everything is the same. Now when I run this, you see now this is more interpretable. It says for people who are at mean of age and time zero, their job satisfaction is 3.2. As time increases by 1 unit, you have job satisfaction increasing by 0.05, and for 1 unit change, that's you see the coefficients are the same, they will not change. For 1 unit change in age, we were getting 0.033 earlier also, we are getting 0.033 now also. But this intercept has become more interpretable now. Now I am going to predict slope variation model dot 6, and I say 1 plus time plus age mean centered plus time into age mean centered. So I have introduced the variables direct effect as well as their interaction. I do this now, model dot 6, I report the summary, and you see now this is also significant at p less than 0.05. So interaction is significant, though it is negative. A negative interaction means that job satisfaction will increase for older people, but it will increase at a lesser slope. Rate of change will be smaller as compared to people who are younger, because the interaction is, this is a negative moderation. We can compare model 6 and model 5, okay, and we see this is better because you have when we have introduced an interaction term, this is a better. So I have written retaining model 6 as the final model, which is multi-dv regressed on 1 plus time plus age mean centered and time into age mean centered. This is our final model, and this is the final coefficient table. I have written report only T table. Summary model 6, and please report T table and report digits 3 decimal places. So we get the p value up to 3 decimal places also. Right? Now we want to plot this. Okay, so you need time, you need age. Okay, so we for age we report the standard deviation and its mean. The mean is 0 and standard deviation is 6.12. So I create a data frame. I say time is 012 and age has 6 values: -6, -6, -6, +6, +6, +6. So this is a data frame because there were only two variables, time and age. So you need to create a data frame with only two values, okay, two variables. So you create the data frame and then use this wonderful command predict. What is the model? Model.6. Use this data frame and I have written level. So because I want to predict only for overall sample now, so I simply predict multi-TV and then finally I do the interaction dot plot. Time is our x variable, age mean centered uh, is our moderator, and multi-TV is the y variable. When I do this, I get this plot. So you see, it says that people who are older, they generally have a larger, higher job satisfaction, but it does not increase over time. People who are younger, they in general have a lower job satisfaction, but it increases strongly over time, rapidly over time. So people who are younger, they show a rise in their job satisfaction over time, though their starting point is smaller or lower. People who are older, their job satisfaction is generally higher at the starting point, but it does not really increase over time. It remains almost the same. And for younger people, you see it is low value of age. This is high value. This is mean minus 1 SD. This is mean plus 1 SD. Is this okay? You can also report this. So the predicted values are these, and I was telling you that I will show it sometime later, but let me show it right now. So you can create this plot even in Excel, and let me go to right. So you say what is our time? Time is 0, 1, 2. Okay. What is our age? Age is equal to, so what was the mean? Let me also just compute the mean of age. It is very simple. You can plot it in Excel once you know the predicted values that are is giving. So the mean is, you see, mean is 25.72. So I will say age 25.72 plus or minus 1 SD minus 6.12. This is the low value of age, and this is going to be 2 plus. So what is this going to be? 25.72 minus 6.12, and this is going to be 25.72 plus 32.84. And what is job satisfaction? You can write job satisfaction for low values were 2.94 or 95, then 3.05 or 06, and 3.16. And for this is 3.48, 3.4, 8 and 3.49. Right, so I have got these values. Now in Excel, you see I have just copied these values in Excel, written these values in Excel. Now you do insert and do line, right? Insert and you see 2D line chart, and this canvas opens up. Double click on this canvas and it comes, there is select data. This window opens up. Now you add legend, add what is the series? We say age is equal to 19.6 years. What are the values of job satisfaction? This is the value of job satisfaction. And the moment you do this, a line starts appearing. Press OK. Then add another series. You say age is equal to 32.84 years. What are the series values? 3.48, 3.48, 3.49. And you see the moment you click, another line starts to appear. Done. What are the horizontal axis categories? What are the labels? Select this and you say 0, 1, 2, and you see it has become 0, 1, 2. Press OK. Then you see on the left side top there is quick layout. I like this layout number 10, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is layout 10. I really like this. Now you can delete all this. You can click on these lines. You can beautify this chart. Okay. Now you can give access title. What is this? This is job satisfaction. You can say what is X? You can say this is time. The moderator, it has anyways written. You can delete this chart title or you can give it, and you can now click on this. It says no line. You say solid line and you see a line starts to appear. Click on this, change its color, because when we write in our manuscripts we will need black and white plots. Similarly, the X, change its color to black. It has become black. Okay, the text, make the color, sorry, not the line, the text options, go to text options, uh, text fill, text box, transparency, no, 0, yes. Similarly here, change the color to black and you get black. And then this, because in a black and white paper orange and blue will not come, so you must double click on this line and go to line option and make it black, make it black, and blue, make it black. But then how will you differentiate? So you make this dashed and change this also as black. Okay, now this boundary also you can change. You say border no line, and you see there is no border now. Now, if you are writing your manuscript in your Word file, you can, if you want to plot it, you say, for example, let's say you are putting it as a figure, moderation of job satisfaction by job satisfaction growth over time by age, right? This is your chart, this is your paper, and you want to bring this plot, right? So a beautiful chart, beautiful plot comes up. So you don't have to copy the plot that R has made, but you know, because you have got these predicted values, you can simply bring these in Excel and then get a beautiful plot and report it in your papers. So now this can be taken print, black and white. There is no colored line, no orange, no blue. Everything is in black and white, right? So this is how we do the plots. This is how you can make beautiful plots and report it in your research papers, right? So the earlier MLM plots also, the same way you can do this. Just report the predicted values, okay, and bring them in Excel and make the plots. This is the beauty of R. It can really do wonderful analysis, give you all these values just by writing simple functions, and then you can do this. This is what is given in this document. You can read this. He does this, then illustrates this chart that we drew. Then he said, first step is to examine properties of dependent variable, calculate the ICC, and he gets an ICC value of 50, and he says ICC associated with job satisfaction is 0.50, indicating that 50% of variance in any individual report can be explained by properties of the individual who provided the ratings. Then step 2, model time. So he first does linear trend, okay, by modeling a linear relationship, okay, and then he adds a quadratic relationship. Then model the slope variability, okay, so he now adds model 2, and he says update model dot to random time and subnum. Then modeling error structures, L1 error structures. So you include correlation, this lag 1 error structure, okay, and then you bring in the, yeah, he then be degree to which the variance of responses changes over time by using this var exponential option. So he says weights is equal to vary exp. And then, so he says in subsequent analysis, however, consequently, we elect to use model.4 as our final level 1 model. With the completion of step 4, we have exhaustively examined the form of level 1 relationship between time and job satisfaction. This analysis has revealed individuals vary in terms of their mean levels of job satisfaction. There is linear but not quadratic relationship between time and job satisfaction, and the strength of the linear relationships vary among individuals, and there is significant autocorrelation in the data. At this point, we are ready to add level 2 variables to try and explain the random variations in intercept and in time job satisfaction slope. So he first brings in age, okay, and then he writes this time plus age and random. This is the command. And then he brings in age for both intercept and slope. And he writes this time into age. So when he writes time into age, this automatically expands to 1 plus time plus age plus time into age. Okay, this is a short form of writing the same thing. And then you can plot this. You see, 32 years old, 20 years old, 26 years old. We have produced an even better graph than this. So once you get this, you can predict this. Okay. So this is how we do this in R. Let us now open our SPSS data and I will demonstrate the entire run in SPSS. So we go to our this data set and I will open this okay, so actually it is not there. So first let us SP launch our SPSS. Right. So once it opens up, we will load our data. So I will read it from the CSV file that I have written back from the R environment. So I will change this to CSV and I say please grow dat.h. Okay. So it says load this, yes. Variable names are included at the top of the file, yes. Okay. And variables are delimited by a specific character, comma. Okay. Each line represents a case, all of the cases, yes. Comma separated, okay. Subnum is okay. We can change the variable name, but I will keep it as it is. And okay, the file is opened. So I have to close the Excel file. SPSS has this interesting feature that if the Excel file is open, it does not read it. So I will read it again. Okay. Next, are variable names included at the top of the file? Yes. Next, each line represents a case, all of the cases. Next, comma separated. Next, variable name, right? I can, instead of subnum, let us call it as ID. And would you like to paste the syntax? Let us say yes and finish. So now I have reading. I will say please grow, right? And let me now run this command. And I have got my data. Okay, so my data, and this is how you would typically arrange it, right? I was telling you, you will arrange it in row wise. So you will say, this is my first respondent, this is his or her age, and this is job satisfaction at time 1, job satisfaction at time 2, job satisfaction at time 3. So remember, the first thing that I told you is we will have to change this from horizontal data to a vertical data format, right? How will we do it? Go to data and restructure here. Okay, restructure. So first it is saying please save this. So let us save it as, let's call it as grow dat underscore h. Okay, I have saved this as grow dat underscore h. Now data restructure. Once you click on restructure, restructure data wizard opens up and it says, what do you want to do? I say restructure selected variables into cases. You see, horizontal to vertical. This is what we want to do. Horizontal to vertical. This is what it is showing diagrammatically. I say next. How many groups do you want to restructure? I have only one group, job satisfaction. So I say one and I click next. Use group identifier. What is the identifier? ID. So I say use selected variable and I want to bring in ID, right? What is the target variable? What are the three variables? Jobs at 1, jobs at 2, jobs at 3. And what is the target variable name? I want to say this is my job satisfaction, JSAT. And what is the fixed variable? Fixed variable is a variable which is, it says, you can read it also. Optionally, you can also choose variables to copy to new file as fixed variable. I want age also to come into the new file, so I will put it as age. Then I say next. How many index variables do you want to create? I want to create one index variable, right? Time. I want to create a variable time also. So it says sequential numbers, index values 1, 2, 3. I call it as index. It is okay. I say next, right? Or I can change this as simply index rather than saying index 1. I say index and next. Okay, drop variables from the new. Keep handling of variables not selected. I say keep and treat them as fixed variables. Okay, if there's anything, please copy them in the new data file. Okay, and then next, what do you want to do? Restructure the data now or paste the syntax? So I say paste and paste the syntax. Okay, so where is my syntax? Here is my syntax. I say now creating, preparing the data file, changing from horizontal to vertical data file, data format. I run this now. Okay, and you see a new data frame has been created. Okay, ID, age has been repeated thrice, index has been created, job satisfaction, which was horizontally arranged, is now vertically arranged. I save it as, don't save it, otherwise it will rewrite the horizontal data. I will now call it as growdat underscore v. Okay, so I have this data file now ready. The only thing left is I have to create a time variable because I need to code it as 0, 1, 2. So I simply say data and I say, sorry, transform, and I say compute variable, and I create a new variable time is equal to index minus 1. I paste the syntax and I say creating a time variable. Okay, I run this and you see a time variable has been created. Now I have to also create, remember this slide where I said that we have to create, because we will test time and time square, so we will have to do orthogonal coding. So we will create orthogonal time and orthogonal time square, right? So let me first compute variable. Let me say time square is nothing but time multiplied with time, right? Time multiplied with time, and I say paste, and it is, I am saying creating time square variable. I run this, and now you see you will get 0 is 0, 1 is 1, and the square of 2 is 4. Now I say data, and you see here transform, recode into different variable. So I will say input variable is time, and output variable I will say auth time, and right, change, and I will say old and new values. The old value is 0, the new value is, what does the slide say? -1, -1. Add, the old value is 1, the new value is 0, and the old value is 2, the new value is 1, right? That is what we had, -1, 0, and 1. Correct. Continue. Okay, and then I say time square, bring it also, and I call it as auth time square, change. And what are the old values? The old value is 0, the new value is 1 minus 2, 1, so it is 1. Okay, okay, so it is there, so I will change this to 1, change. Then I say 1 is to be coded as -2, change, and 2 is to be changed to 1 minus 2 and 1. Correct. Continue. And I paste this syntax. So I am saying now in the syntax I am saying, no, something has gone wrong. Let me do it again. So I say transform, recode. Let us do it actually one at a time, right? So old and new values are remove, remove, remove. So old value was 0, new value is -1, add, old value is 1, new value is 0, right? Yeah, 0, add, old value is 2, new value is 1. Continue, paste. I say, I will remove this. I say creating auth time variable, -1, 0, and 1. Correct. So you see our auth time data has come. Then I go to again recode into different variable. I say I remove this, and I say time square into auth time square, change old and new values, remove, remove, remove. Old value is 0, new value is -1, No, 1 minus 2 and 1 minus 2 and 2 is, let me check again, 1 minus 2 and 1. So I paste the syntax and I say creating fourth time square variable. You see, in R we did not have to do these things, it automatically took, but when we are doing this in SPSS, we will have to prepare this data file, and something has gone wrong because I know what mistake I made, because this is not 2, this is actually 4, because there is no 2 in Times Square, it is 4, 0, 1, 4, right? Continue, and I paste the syntax. This should be the right syntax. 0, 1 and 4. There is no 2 there in orth time. Correct. Now we have got orth time and orth time square. Right? This is all you will need to do for data preparation in SPSS. Now that we have done this, we can begin with our analysis. We will start with mixed models and linear. We will start with our null model now. Null model, now you will have ID as subjects, and now repeated, you see repeated measures, because this is repeated, so you will bring in time as repeated. And the moment you will bring in repeated, you will see repeated covariance. This is the L1 covariance matrix. So by default, it takes diagonal, okay? Diagonal, that there is variance in diagonal, okay? We can keep it as it is. You see there is AR1, there is AR1 heterogeneous, there is compound symmetry, there is diagonal, there is scaled identity also, there is unstructured also. By default is diagonal, so at the moment I will keep it as diagonal. Okay, we will change the error structures later. Continue. What is the dependent variable? It is, okay, why is it string? Let me, we will have to code this to numeric. Okay, age, we will have to code this to numeric. Yeah, this is all. Now they are all numeric in nature. So we will go to analyze, mixed models, linear, repeated time, continue, JSAT, dependent variable. There is no, because we are running the null model. Then we will do fixed. We will say include intercept, continue, random, we will say include intercept, and it varies per ID. Continue, estimation, maximum likelihood, continue like we were doing in MLM, statistics, parameter estimates, okay, covariances of random effects, covariances of residuals, continue, and we paste the syntax. Now this is, we are now ready, and we are running the step 1, running the null model. Okay, let us run this. Okay, you get your AIC, we can write this, you get this, right? Repeated measures, variance, repeated measures, and you get this, and here. Because it has, yeah, all right. Now, because it has taken diagonal, it has given us three variances, okay, not one. So what we will do is because we want to compute, we will change it to scaled identity, that there is only one, right? Remember this slide where I had said what is scaled identity? That there is one variance and it is the same at all times. So we will do this as when we are running the null model. Where did it go? Analyze. Okay, we will change this to scaled identity, continue, and now everything else the same. And I will paste the syntax and I will erase this and I will keep this and I will keep this as scaled identity. Now when I run this, you will see you have got the variances at L1, okay, 0.4319 and at L2, right? So what is going to be your ICC1? ICC1, let us open a new file. ICC1 is going to be equal to, let us open the output window, is equal to 0.4326 divided by 0.4319 plus 0.4326, right? Intercept variance sigma square u0 divided by sigma square u0 plus sigma square r, okay, and we get this, which is equal to, let's copy this here and put a equal to before it. You get 50%. ICC1 is 0.50. This is what we had got in R also, that our 50% variance in job satisfaction can be attributed to our uh, level 2, right? We can also report the fit statistics, AIC, BIC, deviance, delta deviance, and del df, and right. So this is our null model. You can report your, what is your AIC? AIC is 3454.209. BIC is 3469.933. Deviance is 3448.209, and DF is the number of parameters, which is 3. Okay, now let us bring in time. So we go to analyze linear effects, okay, continue, and we bring in time. At the moment we can bring in time because we have not brought in time square, so that is fine. So we bring in time. Oh, sorry. Analyze mixed models, scaled identity, time, fixed effects. We bring in the main effects of time. Continue, random. It is still random intercept. So continue. Estimation is okay, and you paste the syntax. So this is step 2. modeling time trend, and I say this is linear time trend. I run this now. Okay, let us first report our fit statistics. So this is linear time trend. You have 3450.519. BIC is 3471.484. Deviance is 3442.519 and parameters are 4. Delta deviance is going to be this minus this. Delta DF is going to be 4 minus 3. Is this significant? P-value. This is going to be chi-square distribution right-tailed is comma. It is significant at p less than 0.05. Now we get this. This is similar to R. We were saying that job satisfaction increases by 0.05 for every 1 unit change in time, and it is significant. Let us now bring in our time square. Okay, so this is okay. And now covariates, we will bring in orth time and orth time square because we want to bring in orthogonal time factors. We will add their main effects, time plus time square, continue, random, nothing is to change. Okay, everything else remains the same, and I paste the syntax. So I say step 3 is modeling time and time square quadratic, and I run this now. Okay, so let me report the fit stat now. Quadratic time trend. What is the AIC? It is 3451.221, 3477.428. Deviance is 3441.221. DF is 5. Delta deviance compared to the previous model, it is this much. Delta DF is equal to 5 minus 4. Is this significant? You see, in R also we have got this. There is no significant difference. And if I go to the output, I see that orth time square is not significant. Orth time continues to be significant. So we can conclude very clearly that there is no quadratic trend, there is only a linear trend, right? So that is a good news. We just stay with linear trend just like in R. And so we now go to our model again, and we remove orth time and time square and simply work with time. Now what do we want to see? We want to check our L1 error structures. So let me first do this again. Now scaled identity we have got. Okay, what we want to change this now to autoregressive covariance function 1. Okay, no, sorry. First, we will also check. Let us also check. Yeah, I was doing it correct. That we want to check whether there is a random intercept as well as random slope model, right? So we will include time as well as include intercept in both random intercept and we will call this as unstructured L2. So this is unstructured L2 and random intercept as well as random time with scale identity as the L1 structure. So now I do this and I say step 4 linear time trend L1 scalar identity L2 is unstructured linear time trend and this is random intercept and random slope, right? This is, if you look at what he had done when we do, so after we do modeling time we have to do modeling slope variability, and after we do that then we will model L1 error structure. So at the moment we are modeling the slope variability, random intercept and random slope. So I will now run this and I report this in my fit statistic. I say linear time trend. Let me copy the comment that I had written here. Okay, does not copy. So it says linear time trend and let me wrap this. Yeah, this is scalar. So what is the fit? The fit is 3423.603, BIC is 3455.051, deviance is 3411.603, and the DF is 6. So what will be the delta DF? It will be, if you compare this with linear time trend, and what will be the, this will be 6 minus 2. This is highly significant. So this is what we have proven, that random slope is actually good. Random intercept and random slope, linear time trend, and these were all random intercept only. Let us also write this, random intercept only, right? Okay, so these are all correct. Okay, now we will model. So L2 is unstructured, is fine. We will now change the L1 error structure. So we go to analyze, model, and now instead of scaled identity, we will check AR1, L1 error structure. Continue, this will be the same, fixed is the same, random is the same, nothing is to be changed, and I paste the simplex. Now I am saying step 5 here, linear trend L1 is AR1. L2 is unstructured. And I run this. Now you see the problem is it says iteration was terminated, convergence not achieved with AR1. Okay, produce. Okay, but for the time being, we can try this. Okay, we can just report that convergence not issue. Let's copy this. Then we say AR1 SPSS fails at this point. I have put a star here. Let's report 3419.327. BIC is 3456.016. Deviance is 3405.327. Parameters are 7, right? Delta deviance we can calculate is equal to this minus this, and df this minus this. Is it significant? Yes, it is significant. So we can say AR is better, but we see there has been an issue with the fit. Anyways, we are seeing that the fit seems to be better, though there is some convergence issue. Let us try with the heterogeneous model also. So we say AR1 heterogeneous. Continue. Everything else is the same, so I will just paste the syntax. And now I will say repeat this comment. Step 6, and I will say AR H1, and I will run this again. This has again found some fit issues. Okay, but I will report the so SPSS we saw R could easily interpret estimate, but this has not been able to do it. 0113471.184, deviance 3406.011, parameters are 9. So if we see delta df, and delta deviance is this, and delta df is 9 minus 7. Is it significant? This is not significant. So we can, like in R, we are saying that ARH1 is actually not making any difference. AR1 is better than scalar identity. So for the time being, we will say we are going ahead with this, though this is actually giving us fit issues. We can try out some other also. We can see, if you can see, there is compound symmetry also here. Okay, you can see there is diagonal also here. You can see scaled identity we have seen. Unstructured is also there. Let us see if it is running with unstructured. Though I doubt if it is failing with AR1, I don't think it will run with unstructured also. Yeah, it is failing with unstructured also. Okay, let me try out, say, what else is left. Say compound symmetry. Let's say this is CS, compound symmetry. This is also failing. Hmm, diagonal. Let us try diagonal. Okay, so diagonal runs. Okay. Hmm, so I will copy this, paste, and it says diagonal. This runs, and what is the AIC 3416.215, 3458.145, deviance 3400.215. Parameters are, number of parameters are 8. Now, if I compare this with AR1 model also, and AR1 was better than scalar identity. If I compare this with AR1 also, 8 minus 1. So I see this diagonal is better than AR1 also. It will be better than scalar identity. So I will, for the time being, let us go ahead with diagonal because it does not give us any convergence issues. So we will go ahead with diagonal L1, unstructured L2. Okay, that is, so you will have to iterate and find out which is better for you, what is working in your model. Now the last step is we will bring in our age as the covariate. Then in the fixed effect, we will first bring in age as the main effect. Okay, at L2, it will be time, and I will paste. So now I will say in my syntax, I will say step 9. I will say adding age as L2 predictor for random intercept. Okay, so age has come in, and I have not mean centered age. We can mean center, and that should be okay. So we will say, I will copy this, and I will say age as L2 predictor for random intercept. So what will it be? What is the fit statistic? It is 3365.281. BIC is 3412.389. Deviance is 3347.281. Number of parameters are 9. What is the delta deviance? It is 34 minus 3347. Our delta df is 9 minus 8. What happened? It's 9 minus 8, and this is highly significant. So we see our age is a good predictor because it has improved the model fit. right? And you can see age, it is saying just like we had got in a R, for every 1 unit change in age, it changes by this. Now I can mean center, okay? I can compute mean centered variable age. So I say age mean centered is equal to age minus mean of age. This is, I'm saying, mean centering age. So I have now mean centered age also, and you can see age underscore what happened. Okay, doesn't matter. Let us report what is the mean of age. Let's just report what is the mean. The mean is 25.72. So I will say transform compute age mean center age minus 7. And once it runs, this is our age mean centered. The last run now is our L1 is diagonal, age, let's bring in age mean centered. So our fixed effects are going to be this, and then I will also have the interaction of time and age. Continue. Random is going to be the same, okay, and I paste the syntax, which is equal to, now let me copy this comment. Step 10, linear time trend, adding A's as L2 predictor for random intercept and random. Now when I run this, I get my final run for random intercept and random. What is the fit? It is 3362.012. BIC is 3414.354. Deviance is 3342.012. DF is 10. What is delta DF? Minus this, and delta DF is this. Our p value is, so this is our interaction. Our this model is also significant at p less than 0.05. So we can say that there is an interaction term. The overall average is 3.21. With every 1 unit change in time, job satisfaction goes up by 0.05. Every 1 unit change in age, it goes up by 0.04. And age is a negative moderator. Just like we have got this. And now you can use this to do the plot. You have your final fit. This is our final run. I am highlighting it in a box. This is your final fixed effects estimate. We can use them and create a plot like this. If we get time tomorrow, I will show you how to plot it even when using the SPSS output, we can use these coefficients. Okay, let us copy this fixed effects. Let me copy this in the Excel file, and if we get time tomorrow, I will show you how to compute this, compute or plot a similar graph. This we showed using R. I will show you tomorrow how to do it in SPSS using SPSS output. Okay, so this is how we do this in SPSS also. SPSS fails at places, but you can try, explore, and then whatever gives you the best fit in terms of L1 error structure, you work with that and move ahead. Right, so I will upload this also in our shared folder. I will upload all the this syntax file also. Okay, let's call it as in longitudinal, we'll call it as syntax job satisfaction. Fine, if there are any questions, we can take them now. Yeah.
So not really a question, just a reminder if you've saved your workspace in R.
Yes, I will save it.
Right. Thank you.
Thank you. And yeah, we will meet tomorrow at 3 o'clock. Now I hope we will be able to finish the second example tomorrow easily. We'll go over all this in R and SPSS, and we'll take it forward. Thank you, and I'll see you all tomorrow. I will upload the recordings and all the relevant files. Okay, take a look, practice, and yeah, the more you practice, the easier it will become.
Thank you very much, sir.
Yeah.
Thank you, sir. Thank you.
Thank you.
Thank you.
Thank you.
Thank you, sir.